Okay, Professor Brandon, ladies and gentlemen, and fellow students, a delightful afternoon to you all. So I'm Dennis Leung from the Department of Mechanical Engineering, and I'm the coordinator of this William Mong Distinguished Lecture today. So we embark a journey of knowledge and inspiration as we gather for the extended William Mong Distinguished Lecture series. So maybe let me just give a little bit background about this William Mong Distinguished Lecture series first. So this series, established in 1991, pays tribute to Dr. William Mong, founder of Sun Heng Group, and his notable contribution to engineering and technology. It serves as a beacon of wisdom, providing a platform for distinguished researchers from around the group to enlighten our community in Hong Kong. Maybe now let me give a little bit background about our speaker today. It is with great pleasure that we welcome Professor Nigel Peter Brandon to our midst. I know Professor Brandon for a few years while we are working together for IOP, the Progress in Energy Journal, where Professor Brandon is the editor-in-chief. And now this journal has a very high impact factors. Professor Brandon holds the chair in sustainable energy, sustainable development in energy, and is the Dean of Engineering at Imperial College since 2017. He received a Bachelor of Science in Engineering and PhD from the Department of Mineral Resources Engineering at Imperial College, London, in 1981 and 1984, respectively. His research interests lie in electrochemical science and engineering, with a particular focus on fuel cells, electrolysers, and flow batteries. Professor Brandon received an OBE in 2011 for his services to UK, China Science, and is a Fellow of Royal Society and the Royal Academy of Engineering, and as well as an international member of the US National Academy of Engineering. Professor Brandon's illustrious career has been adorned with prestigious accolades such as the Kastner Medal awarded by the Society of Chemical Industry, Horizon Prize from the Royal Society of Chemistry, and Francis Bacon Medal by ASME, just name a few. Beyond academia, Professor Brandon has fostered strong industry connections, drawing from his 14 years extensive research experience with BP and also Rolls-Royce. He is also the founder of 3 startup companies in the sector. One of his earlier startup companies is now a listed company in London with a market value of over £400 million. Very amazing. Today's discussion promises to be captivating as we delve into the pivotal role of electrochemical technology in the shift towards low-carbon energy systems. Professor Brandon will share with us his insights from his journey of translating cutting-edge research into real-world applications, focusing on the transformative story of Ceres Power, a relaunched fuel cell and electrolyser company funded from Imperial College of Professor Brandon's group in year 2000. Before we begin, I'm honored to present a token of appreciation on behalf of the Faculty of Engineering to Professor Brandon. And will you all join me in giving a warm and enthusiastic welcome to Professor Brandon? Thank you.
Okay, now I have to talk a bit quieter. So I know there's a lot of interest here in Hong Kong in how you regenerate your fraction of GDP from manufacturing, from the industrial base. And so I hope, at least in the room, for those of you who are still engaged in the research piece, or even those of you who are engaged in funding the research piece, you're giving some thought about how do you translate that to create businesses and therefore jobs in these emerging sectors. So that's what I'm going to try and do in the presentation. I hope to leave some time for some questions at the end. Okay, so I am going to start, however, by picking up on Professor Catlow's theme about decarbonisation, and in particular focusing on electrochemical technology and in specifically hydrogen as a low carbon energy carrier. I'll do that briefly. I'm going to start there because we always have to be aware of why we're doing what we're doing. And whilst today there's more interest in some of the technologies I'm talking about, I've been working in this field for 40 years, and for much of that time people have not been interested in the technologies we're talking about. So sometimes you have to be able to articulate why it's important. I'm then going to talk about 4 different things. One is the work which is with Ceres on solid oxide technology, so a particular type of fuel cell and electrolyser technology. Then I'm going to move on to flow batteries for longer term energy storage. Then I'm going to talk on to a company we actually got funding for yesterday, so we've just closed the seed round, which is all around materials and materials manufacturing and materials processing, which is we see as an enabler for some of these technologies. Then some work we're doing on distributed hydrogen systems, trying to replace propane and butane tanks, and then some personal reflections on commercializing research. So I hope that's, it's going to be quite busy because I've got quite a lot to get through, but we'll see how we get on. So why? So I'm going to show this figure because this is from the UK. And what this figure is showing you on the vertical axis is the flow of energy through the UK energy system. And we'll talk about the UK because it has an economy that's representative of many others. I suspect here it's quite different, and that's okay. But I'm going to use it to make a point. And on the horizontal axis is time. And when we talk about energy and we talk about the energy system, the first thing I want to say is that we often talk about electricity. And that's the red line at the bottom. That's the flow of electricity through the UK energy system. This line, jagged line in the middle, is the flow of liquid fuels, which is essentially gasoline and diesel. And for us, based in a northern European location, which is quite a cold and damp location, this is the flow of energy as natural gas. And that nature of that sinusoidal flow tells you that that's mostly to do with heat. So like a lot of Northern European economies, but not all, a lot of our heat demand comes from natural gas. That's both for heating our buildings, but also for manufacturing and process heat. And this just shows you the scale of the challenge, because we're doing quite well at decarbonising this bit down the bottom, because you can use renewables to decarbonise electricity. But by far and away, the largest flow still is fossil. And so we have to try, how do we decarbonize an energy system when you have these combinations of these really big cyclic loads on the system? So if you're trying to take all of the gas, for example, we use for heating into electricity, and you can do that with a heat pump. A heat pump is a more efficient way of producing heat than burning gas. A unit of gas burnt gives you roughly a unit of heat. A unit of electricity in a heat pump might give you 3 to 4 units of heat. So let's say it gives you 4, let's say it gives you 3.5, that makes the maths easier. This is 3,500 gigawatt hours. If we did all of our heating with heat pumps, we'd need about 1,000 gigawatt hours of extra electricity, which is the same as the entire UK electricity system generates today. And we would only need that for some months of the year. So the cost of that infrastructure becomes extremely high because you're building a very large asset that you're only using for some of the time. So when we look at the energy transition, of course, decarbonising electricity is the key driver for that. and using that electricity, for example, in electric vehicles. But it gets really hard to decarbonize everything with electricity, and that's where you need low-carbon molecules. Professor Cattler spoke about the need for low-carbon molecules for chemistry, which you absolutely need for chemicals. We're going to also need low-carbon molecules for other parts of the economy. So you need molecules and electrons, and that's the theme of why we need to think about that. And the simplest molecule to make is actually to split water and make hydrogen, and that's one of the reasons we're interested in hydrogen. Once you've got hydrogen, you can combine it with CO2, you can combine it with lots of things and you can combine it with nitrogen to make ammonia. So you get a whole chain of chemicals and fuels, all of which start and need hydrogen. Okay. So hydrogen is going to be a bit of a theme through the talk. We, of course, make lots of hydrogen today. The world makes about 100 million tons a year of hydrogen. It makes 96% of that from fossil fuels. It doesn't make it as an energy carrier. It makes it as a chemical feedstock. And Richard spoke eloquently about the need to decarbonize those parts of the economy in his talk. So going forward, we start to think about hydrogen playing a different role. This is a cartoon of the role of hydrogen in the energy system. The blue boxes refer to blue hydrogen, so that means hydrogen with carbon capture. Richard spoke about carbon capture, so you might make that from fossil fuels by pulling off the CO2. That's so-called blue hydrogen. The green boxes refer to what we call green hydrogen, so that's hydrogen made by electrolysis, powered by low-carbon electricity. Often, therefore, renewable power to electrolysis to split water and make hydrogen. And once you've got those hydrogen, of course, the hydrogen doesn't care so much whether it's blue or green. It cares a little bit about what impurities in there, and there is a difference between green and blue. But then the end users can be combined into that to form its application for heat, for example, for transport fuels, or for industrial decarbonization. And this is not my picture, but I like it. And I think when you start to think about the energy system of the future, it's really how molecules, and hydrogen represents those clean molecules, and electrons work together in the most efficient, low-cost, and resilient way to decarbonize the energy system of the future, and therefore, in turn, the services, the industries that use those services. Okay, so I think it's an important picture to have in mind. Sadly, in this field where there's a lot of advocacy, people can knock hydrogen or they knock electricity. In fact, you need all of the above, and it needs to work together. So it's not one being better than the other. It's about playing to the relative strengths of the different approaches, and I'm happy to discuss it if you have questions. Okay, so that's the context, right? This matters, and it's going to matter at scale. So let me get on to my theme of, if you like, technology innovation. And I'm going to start with the solid oxide technology, and I'm going to show this picture. So I'm going to talk about fuel cells, and I'm going to talk about electrolysers. Many of you work in this area, but not necessarily all. So let me start with this cartoon. So a lot of you, I know, work on low temperature systems, so-called PEM fuel cells. I'm going to talk about those tomorrow. I'm not going to talk about those today because I haven't been directly involved in commercializing those. But in a PEM system, we put hydrogen in on one side, we have a proton conducting membrane, and we put oxygen in from air on the other side. And when the two sides of the cell are connected together across a load, we can allow hydrogen oxidation, oxygen reduction, electron transfer around the external circuit, which of course is the flow of electricity, coupled with proton transport across the membrane. And that's what gives us a fuel cell that will produce power. It produces DC power. There is no combustion reaction, so we don't get NOx. We're not getting any other, is this all right on volume? Yeah? Okay. We're not getting any other products of combustion. So it's a very efficient way of taking a fuel into DC power. Far more efficient than a heat engine of the same size. And importantly, fuel cells, like any electrochemical technology, maintain that efficiency more or less irrespective of scale. So a very large, if you're looking at heat engines like gas turbines or internal combustion engines, Small heat engines are inefficient because they lose heat, broadly speaking, and they have a lot of mechanical friction relative to their size. So you tend to get a significant drop in efficiency as you go to small scale. So if you want a 1 kilowatt machine or a 10 kilowatt machine or a 100 kilowatt machine, they tend to be quite inefficient. Whereas a fuel cell maintains that efficiency right through the 1, 10, 100 megawatts range. So you get a lot of a good efficiency profile if you're in power generation mode. I'm going to talk about this technology, solid oxide fuel cells. It's the same principle. We put a fuel in on one side. I'm showing here hydrogen, but that fuel can also be methane or it can be carbon monoxide. But shown here is hydrogen. Hydrogen is oxidized. Put oxygen on the other side, oxygen is reduced. But now the membrane is an oxide ion conductor, not a proton conductor. So when the circuit is closed, current will flow, electrons will go around the external circuit, but oxygen ions will cross the membrane, where they will combine with the hydrogen side to produce steam. So in a PEM, you get water formed on the air side, and in a solid oxide, you get water, in this case, steam, because these are hot on the fuel side. So that's the principle. And the challenge is around how you engineer durable, scalable devices. Now, these types of technology, which is what I'm going to focus on, generally run, certainly when we started in this field, they run about 800 to 900 degrees centigrade. And the oxygen ion conductor is a ceramic. So it's a rather delicate ceramic material. And the question is, how do you ensure and scale up devices that don't have failure of those ceramic materials? So a brief comment on fuel cells. So fuel cells have been around a long time. And the joke in the fuel cell field is that they're about 10 years from commercialization. They always have been and they always will be. In other words, they've never quite made it. But now people are selling actual fuel cell products. This shows you some products in the US from Bloom. That's a Ballard PEM fuel cell stack, which you can find in fuel cell buses and other vehicles. And that's a product in Japan containing the Ceres technology that I'll talk about. And you're starting to see sales actually going out. And in fact, this is the last year that this report was made available, unfortunately. It's a very useful report of the Fuel Cell Industry Review, and it shows 2.5 gigawatts of power products sold. So that's fuel cells. I'm also going to talk a bit about electrolysis. So electrolysis for water splitting, as I've mentioned, is an important way of making green hydrogen. This is a nice paper from a German group, and it just paints a picture between the different, in a simple way, between the different electrolyzer technologies. So when we think about splitting water with hydrogen, the biggest cost is the cost of the power. 60 to 80% of the cost of making green hydrogen is the cost of the electricity you use to make it with. So this number here, which is efficiency, matters a lot. The more efficient it is, the less power you need. These are, broadly speaking, the three leading candidates today for electrolysis. There is a fourth one, which is alkaline membrane electrolyzers, which I think are very promising, but are not shown on this figure. These are PEM electrolyzers, so a little bit like a PEM fuel cell, but operating in electrolysis mode. This is the alkaline electrolyzer, which is very mature. It's been with us for 100 years. And that's the high temperature electrolyzer that I'm going to talk about. And on this lower curve down here is what's called current density. And any electrochemical reactor, the current density is the reaction rate. So this is reaction rate. So this is effectively the amount of hydrogen you're going to make per unit size of the reactor. So the bigger the number, the smaller the reactor, and therefore the lower the capital cost. And this is efficiency. The bigger the number, the less power you need, the lower the operating cost. That's roughly how it translates. And this is a review of showing that PEM electrolyzers are very good at giving you lots of high power density. Alkaline electrolyzers, which are the most mature, sort of occupy the least attractive space. And solid oxide, because of the thermodynamics, which I'm not going to go into, give you the highest efficiency. So the question is where in this space you can sit. Lots of people developing these technologies. This is the one I'm going to talk about. And I'm happy in questions to explore the differences. So if we look across a typical solid oxide cell, This is the type of what it might look like under an electron microscope. So this here is the electrolyte. So this is your oxide ion conductor. The scale bar there shows you that that's about 120 microns thick. So that's about a human hair. That's the type of thickness we're dealing with. On top of this is an electrode for the oxygen reaction. If it was in fuel cell mode, it would be oxygen reduction. In electrolyzer mode, it's oxygen production. And this is the bilayer structure for the fuel electrode or the hydrogen electrode. In electrolysis mode, obviously, you're putting in steam and producing hydrogen. In fuel cell mode, you're putting in hydrogen and producing steam. But that's the type of structure that is quite conventional. Now, they work. Companies like Bloom will sell you cells that produce stacks and systems with cells like that. But the biggest disadvantage of this is that whilst I said that's about the thickness of a human hair, that's still quite thick in terms, because the resistance of this cell to the flow of ions is dominated by the oxygen ion current across that material, right? That is by far and away the biggest resistance in the circuit. And resistance means loss of power, or it means inefficiency. So resistance is basically cost. We want the resistance to be as low as possible. So we can do that in two ways. We can change the material to something that has a better conductivity, or we can make it thinner, or we can do both. Now, the challenge with making it thinner is how do you mechanically support it, and the challenge with changing the material is to what. But that's what we did that underpinned the technology that's behind Ceres, which is this company I'm going to talk about. So where did this idea come from? It came from a research proposal to the Science Funding Agency in the UK. It's called EPSRC, the Engineering and Physical Sciences Research Council. I'd arrived at Imperial College in 1998, having had a 14-year industrial career, and I collaborated with these very experienced academic partners down here, Brian Steele, Alan Atkinson, and John Kilner, and a research officer called Bob Rudkin. And we had a grant, and this grant led to this idea of the fact, well, actually, if we want to make these cells thin, we'll need a mechanical support. And there are other people who have thought about having a mechanical support, and most commonly they use one of the electrodes. But the electrodes aren't that mechanically stable. So why don't we use a metal? A metal is much more mechanically stable. So why don't we have an idea where we have a metal support with some holes in so we can get gases in and out, and we put our materials on top of that. So we have our anode, our electrolyte, and our cathode. And we produce a very different type of cell. We should produce what people call a metal-supported cell. And this was the patent that we filed with that concept. Okay, so we have a simple concept, and we filed a patent. And we tried at the time to persuade industry partners that this would be a great idea. They could work with us and license this idea. But it was so different to the way everyone else was making solid oxide fuel cells, and actually largely is very different still today, that no one wanted to license it. It was too different to what they were currently doing. So to take the idea forward, we decided we need to create our own company and raise our own money and develop our technology ourselves. So that's what we did. So these are the people involved, and I have to pay absolute credit to them, because these things are always a team effort. And I was very much the junior member of the team, actually. And here you see me looking no younger than no, I've not aged a bit, as you can tell. So this is Brian Steele. Some of you will know Brian, the late and great Professor Brian Steele, one of the founding fathers of solid-state ionics, who was involved and really a key force in this. I have to tell you a personal story. When we set Ceres up, we had to put some of our own money into it. Not a lot, but we had to put some in. My wife's sitting here. We'd just moved from the Midlands, which is a cheap part of the UK, to London, which is the most expensive part. And had two small children. I had no money. And Brian lent me the money that we put into Ceres. He just said, here you go. So, and I eventually paid him back. But he was, but he just lent it to me. This is John Kilner. Some of you will know John. A very senior guy in the field as well. and this is Alan Atkinson. So in fact, John was Brian's postdoc a long time ago, so this is how the whole thing's connected. And there's me in there. So I have to pay reference and acknowledge all of those efforts. So when you're thinking about, so this is my story, and I think stories matter in this area, right? So the IP, the patent, came out of a science project. It was a science project, though, in which we always had a vision for why we wanted to do this innovation. And I'd say a theme throughout all of the work I'm interested in and tend to get involved in is to say, how do we try and solve a technological challenge through some materials innovation? Rather than saying, I've made some interesting material, how do I now use it? Which is a valid approach, but not the one I tend to take. So how does this unlock? So we knew that if we could make, we felt that if we could make these metal-supported cells, by the way, we had no way to know how to make them, that it would unlock some technology advantage. So we formed a team. I was asked to be the CEO. I was the most junior academic in the room, and also I'd just done 14 years in industry. We took on this guy, Philip Holbeach, who is a finance guy. He's not technical at all. And I think for any of you in the room who are interested in forming a company, you do need some financial acumen in the team. We raised £4.5 million, so $45 million back in 2001. It was a lot of money, still a lot of money. It was a real lot of money then. And we'd had some MBA students work with us on the business plan. Those MBA students had won the European Business Plan of the Year competition with the Ceres business plan, and we hired 2 of them. And we hired a full-time CEO in 2003. Brian sadly passed away in 2003, very early in his 70s, really far too young. And I took on Brian's job, which was the technical director, and I did that for 3 years. Then I became chief scientist for 3 years, and then I exited. I left the company. In fact, the company said, we've had enough of your services, thank you very much. And we parted company. We listed on the alternative investment market, which is the NASDAQ type market in London in 2005. Okay. So this is some photographs that you can find, just showing you what this looks like. There's a piece on the internet about it. This is what the cell looks like today. You saw me holding that square sheet. Now you see it looks far more sophisticated. It's got integrated sealing ports. It's got integrated flow fields. And this is what is now the development line, not the production line at Ceres facilities. And that's what it looks like. It's very boring, right? It's just a load of plates all stacked together. Now, anyone who knows about high temperature fuel cells, no one else makes them like this. So a PEM fuel cell looks like this. In other words, it's a load of plates interleaved with interconnects and bolted together. When you make something at 800 degrees C, you cannot do that. And that's because metals creep at temperature. So you can't use bolts at 800 degrees C. It's not possible. Yeah, you can put things in compression, but you can't bolt it together. Now this is at 600 degrees C. And it's at 600 degrees C because we've made it thinner, and we used a different electrolyte. We've used a doped gadolinium oxide. We heard about ceria earlier. If you dope ceria with gadolinium, or indeed some other ions, you can create an oxygen ion vacancy, and then it becomes an oxide ion conductor, and it works at 5 to 600 C. A diesel engine runs at that sort of temperature. So all of the metals are the same you can use in diesel engines, with some constraints about thermal expansion coefficients. So you can bolt it together. You can have gaskets. The whole thing becomes a lot simpler to engineer. And that's really the whole point. So by thinking through the materials, you've solved, or certainly made the engineering easier. So this is what the cell looks like, right? So from that core patent, this is some of the details are obviously not on here because they're not, the company don't talk about all of the details about what the materials are. But this is the steel. It's a ferritic steel. It's laser drilled to give it porosity. The anode is a mixture of nickel and doped ceria, porous. The electrolyte is a gadolinium doped ceria. In fact, the electrolyte is a bit more sophisticated than that because the doped ceria can be reduced in a fuel environment. And if you reduce it, it requires some electronic conductivity. So in fact, we have to put in a blocking layer. So we put in a layer here of something that's not, it's an ionic conductor, but it's not a CGO, and that blocks that electronic conductivity, the residual, and then a cathode that's not disclosed on the air side. So that's a lot of development to get to that point. The other key point down here is this one, right? So the whole point of making a metal, quite frankly, is it allows you to have a gasket, a welded and gasket seal. And that welded and gasket seal sits at the heart of the benefits of this approach to robustness. When I say to people, if you work in high temperature materials, the electrochemistry is relatively simple. It's so hot, the charge transfer reactions just go like that compared to low temperature. But it's really a mechanical engineering challenge. How do you get these different layers to be bonded, to adhere to each other, and to allow things to be sealed, and for those materials to sustain thermal cycling? So, part 2 of my story, right? So Ceres did very well. It grew. It listed in 2005, to remind you, on the stock market. But in 2012, it really hit a very public once you're listed, everyone knows your business because you have to say to the market what the situation is. And there were some trials of a unit in people's houses which didn't work. The market lost confidence in the company, and its valuation fell to under $1 million, which was less than the value of the cash in the bank. And it was very close to just being shut down. So I was asked to come back in as an advisor, and the business and an investor came in from IP Group. IP Group are a venture capital company in the UK, based actually globally, but founded in the UK, who specialize in early stage technology investment, and they came in, recapitalized the business. Of course, when you recapitalize a business like that, anyone who's a shareholder gets completely wiped out. That's a sad fact of life, because they issue a load more shares. So where you may have owned 10% of the company, you now own 0.1% of the company. But that's how life is. This is the joy of these things. And the company model changed from developing a product, because at that point the idea was we'd develop everything, which was naive, to a model in which we became a technology licensing business. So we would license the technology to others to manufacture at scale. Of course, you lose some of the upside, but you reduce the capital requirement. Now, that has aligned with an increasing interest in the space. The company's value goes up and down, so it's somewhere in the 350 to 400 million pounds. So 300, well, it's at $3.5 billion, I guess, to $4 billion today. You can buy shares in it, but please don't take that as advice. I'm not allowed to give you financial advice. And it has some major partners, right? So the key in this is now to have identified potential partners who are going to both invest in the business and take the product. Bosch you will have heard of. That's the big German company. Doosan are a Korean company. Weichai are a Chinese engine manufacturer, and Miura are a Japanese boiler manufacturer. And there are some other partners as well now. As well as all the fuel cell stuff, along that journey, people have become more and more interested in high temperature electrolysis, because they've become more and more interested in hydrogen production, and the most efficient way to do that is high temperature electrolysis. So not only does the company have this fuel cell product range, it also has been thinking about electrolysis. Now the challenge is in fuel cells you can make perfectly useful products at 10 kilowatts and 100 kilowatts, but really no one wants a 10 kilowatt electrolyzer. They want a megawatt or a 10 megawatt or a 100 megawatt electrolyzer. So it's all about thinking scale differently. So this is the Ceres 1 megawatt electrolyzer. That's now in India with Shell in Bangalore. So we've gone from something that was in our labs that was perhaps a square centimeter to something now being tested in India by a major corporate. And as you can see, you know, the scaling here. So we've now gone through some more substantive engineering. So this is the company listing on the stock market, in the main stock market in 2023. So it's on the main market now. And this is the team. So I think the other thing you can see is that going from a postdoc and a PhD student, which is where we started, to about 500 people, which is where this photograph was taken at a Ceres kind of celebratory event, shows that there's a lot of people involved in this endeavor. And therefore a lot of money, because that takes a lot of cash. But it shows what you need to do to get things moved along the journey. We had a question earlier about how do you take basic fundamental catalysis advances to scale. Well, what you need is probably a few £100 million and 500 people. Okay, that's what you sort of need. And a lot of belief and hard work and people's efforts. So I'll try and show a couple of slides on what we do back at Imperial. So we still have research in this space. My group's been very interested and still is very interested in electrode structures and how you design electrode microstructures for performance. In high temperature, that can be quite tricky because if you make the classical kind of high surface area wash-coated catalysis type approaches, everything sinters and moves around and you lose surface area. So we're interested in that. If anyone wants to talk to me, you're welcome to. We also get involved in a lot of modeling. So we don't do the DFT end of modeling. We do, if you like, what I might call the engineering continuum scale modeling from materials through cells to stacks to systems. And that's a very talented postdoc who's leading our transient dynamic modeling of, in fact, reversible cells, because high temperature cells can be driven in fuel cell mode and electrolyser mode just very simply. You can just switch the polarity and you'll reverse the stack. Okay, so let's move on. So let's talk a bit about longer term energy storage. For those who were really quick at watching Richard's slides, you would have seen there was a nice Royal Society report on longer term energy storage recently. It was in your list, I spotted it. And I commend it to you. we're particularly interested in this area. And so why are we interested in longer term energy storage? Batteries, lithium-ion batteries will do everything, right? And of course, they're very good lithium-ion batteries. There's lots of things they'll do. Sodium-ion batteries are coming through, and there's lots of things they'll do. But once you start to store 8, 12, 24 hours of energy, it's not so clear that that's the most cost-effective solution. This is a report from California looking at the forecast for California's long-term storage needs. And in California, it'll be a photovoltaic approach, PV. And of course, if you go for very large-scale PV, you end up with lots of power in the day and nothing in the night. So their forecast is they need about 10 hours of storage. This is some data from the recent German experience. So again, those of you, I'm sure who follow the news will have, Russia has invaded Ukraine. Russian gas, Germany is no longer taking Russian gas and has had something of a crisis about where it gets its power from and rushed into, it already had a high installed base of solar photovoltaics, but it's rushed into even more. So these green lines here, the green bars, are the installation of solar PV in Germany that year. And this is the cumulative installed capacity of solar PV, and this is German energy demand. So there's a lot more PV and a lot less, more than demand. And of course, as a consequence of that, and bearing in mind that you can't produce power at night, this is the euros per megawatt hour paid by the market. The blue line being the standard power paid. And get my color right, doesn't really matter, but the purple line being what they pay for solar. So solar power producers are getting 13% of the average, which is killing the solar power producers. Why? Because they've got so much excess capacity in the daytime that the system doesn't want or even makes them pay to take. So it's killing it. So this is the market for longer term storage. If you can firm this up by storing it, you can sell it here. Right? And that's there's the market opportunity. So we've been interested in flow batteries for a while, right? So there are a range of technologies that play into this longer-term storage space: compressed air energy storage, liquid air energy storage, being two. But we're electrochemical engineers, we're interested in electrochemical solutions. And for those of you who are aware of flow batteries, this is the cartoon of the current incumbent, it's known vanadium flow battery technology, in which in a flow battery you have two tanks which store a redox couple and an electrochemical reactor which changes the oxidation state of that redox couple. So when you want to store energy, you have, in this case, a vanadium couple, and you change the oxidation state from 4 to 5 on the one side. You produce an oxidant, and you produce a reductant by going from 3 to 2 on the other side. And when you want the energy back, you just flow those through the same reactor, and it goes into fuel cell mode and generates the power. It works very well. They're about 80% round-trip efficiency, less than a lithium-ion battery. But because when you need more energy, you just have more vanadium electrolyte, and you have a bigger tank, these get cheaper and cheaper the longer you want to store the energy for. So ultimately, they win out. Now, the challenge with vanadium, which is around, and lots of vanadium flow battery companies have gone bust, is because A, we don't have a market today for longer-term storage. The market is all going to be in a few years' time. And B, vanadium is very expensive. Its price is pinned by steel making, in fact. And okay, depends where you are in the world about your view on whether this is an issue. Most of the world's vanadium comes from China and Russia. So not every country is happy about that. So there's a security of supply question and a price question. So the question is, can you do something that's not vanadium? And that's what we've been thinking about. So we've spent quite a lot of time thinking about different redox couples. But the other thing we've done, and this is collaboration with my colleague Antony Kusinak, who's in the chemistry department, and Antony is a top kind of electrochemist and electrocatalysis guy, is to say, well, what can we know a lot about fuel cells, actually. We know a lot about electrolysers. Actually, we could think about using hydrogen as one of our couples, and we could pair that gas phase reaction with a liquid phase reaction, rather than having both liquids. Why would that be attractive? Well, you always get some crossover across this membrane, right? Now, if it's all vanadium, it doesn't matter. You get some inefficiency, but at the end of the day, you're not getting any cross-contamination. But in a number of chemistries, you use different species on both sides. And if they're both liquids, they start to mix. And then that becomes a real challenge in electrolyte quality. But if one's a gas and one's a liquid, if we get a bit of crossover, it's really simple. The liquid just drops out and you just re-inject it back in. This is a very facile reaction. It's very fast. It gives you high current density. That's good. You're talking about hydrogen in a closed loop. It's not high pressure. It's probably up to 10 bar. It's not like a 700 bar tank for a car or something. And we've settled on manganese for the liquid phase. Manganese is used in all of the little primary batteries you've got at home. It's produced, it's the 12th most abundant element, and it's widely available. Now, the challenge with manganese, however, in acidic solutions is that it disproportionates and it forms manganese dioxide, which precipitates. So you have to stabilize that. And so we found a way to stabilize that so you can stop that happening, or you can certainly control it. You can enter operating regions where you can form it, but you just, once you know where they are, you don't go there. So that's good, right? So we've got manganese and hydrogen. We can also think, well, actually, in the future, if we had hydrogen more available, we don't even need a hydrogen tank. We can just have this connected to hydrogen pipelines, and we can just charge and recharge our battery. The round-trip efficiency of this is about 80%. So you get about 80% out what you put in. Now, if you're comparing that, for example, to an electrolysis fuel cell combination for doing the same job, an electrolyzer is perhaps 70% efficient. A fuel cell might be 70% efficient, round-trip efficiency at 50%. So you're significantly more efficient. So that's the end. And it works. So we've published work on it. You get high power densities. Now, if you're a fuel cell person, these are not high power densities. But if you're a flow battery person, these are amazing power densities, because they're much lower because of mass transport limitations, usually, in a flow battery. So we formed a company in 2018. This is a much more embryonic story. That's the team. There's been a couple of people changes since that photograph. There's some patents, and there's a couple of nice papers that show that it works. Ørsted have selected the company for some trials, so that's very exciting. Ørsted are the big renewable power company based in Europe. And this is today. So this is the prototype system demonstrator. You can't see the tanks, they're behind it. But you have to go through the chemistry. We've done a lot of chemistry, Anthony's group in particular, on understanding the manganese speciation. It's quite a complicated chemistry. To convince ourselves we understand the chemistry. And then you have to do the engineering. So having got that, how do you scale it up? It comes back to that question before. So there's the story, right? Again, it came out of a series of fundamental science projects trying to explore different materials and different chemistries. Right? Picks up on Richard's excellent point, right? Without transformational science, we can't develop new technologies. So it came out of that. We founded it. We hired, so with Ceres, I became the CEO, but now I'm Dean of Engineering. I can't go off and become a CEO. I haven't got time. So we hired, and I'm not a very good CEO anyway, so we hired a proper one, right? Tim von Werner, who came and joined the business. And we raised seed investment. Again, IP Group came in and helped us with that. We're currently based in Imperial College's accelerator. We've now got 10 people. We've demonstrated this system. If anyone in the room has any connections to investors, we're looking for a Series A round of 150 million Hong Kong dollars at the moment. So please.
In Asia,
back in the UK. But we don't mind where the investors come from within reason, as long as they're not Russian. So please, we are genuinely looking for a seed round at the moment, hoping to close in the next few months. I'm not saying that in jest. We genuinely are. Okay. And of course, we still continue to work in this area at the university. So Catalina, you saw earlier, so she's leading a few PhD projects we're supervising on doing some fundamental modeling. You'll see that this is on vanadium hydrogen. Why? Because vanadium hydrogen has almost the same, different chemistry. Okay, so the differences do matter. But from a lot of our modeling, we can do all our model development using a system that we can publish, because we're not commercializing vanadium hydrogen, so we're free to do whatever we want with it. We are working on manganese hydrogen, but we don't necessarily publish it. And then we also do a lot of work trying to understand the effect of, for those of you interested in porous materials, I know there's quite a few, we're quite interested in how the support and the mass transfer in that support then couples to the catalysis. And in flow batteries, particularly liquid phase, they are mass transport dominated. Okay, right. So this is our third one, okay? So this is called M-Spin. We actually signed the papers for the seed round yesterday. So we've just got the money in while I was here. We've been trying to get the money in for a while. It's pretty tough out there to raise money at the moment. And this is using electrospinning to make high surface area materials. Now, electrospinning, for those of you who follow these things, will say, well, that's nothing new about electrospinning. You're absolutely right. Electrospinning is a scalable process. It's used to make lots of polymeric materials, medical materials in particular. But what, through the work of this guy, Mong, who was a PhD student in my group, now a postdoc, and now the CTO of this business, we've developed a way of electrospinning metals. Now, people have electrospun metals before from metal salts, but you get very low solids loadings. Essentially, you produce nothing useful technologically. But we've found a way of taking solutions. This is a photograph from one of our industrial trials. And you can, this particular one is a ball electrospinning, but you can also do it with series of parallel electrospinning needles. And once you do that, you can take, and the invention here is in what you electrospin. So it's the chemistry of the solution that you're electrospinning. That's the clever bit. That's why we've done it completely different to anyone else who's done it before. And I think because we work on solid oxide fuel cell materials, we've thought about it completely differently, because this was started off as an SOFC project. So this is our trial solution, spun by an industrial partner, and we can get 10 square meters of material back from a small bottle of solution. This is Robin Francis, who's joined us as a full-time CEO. He's a very experienced industrialist. He's already exited from other companies. He's a materials guy out of Cambridge originally, a long time ago. And this is some microstructures of the type of things we can make. So these are nickel fibers. So that electrospun mat I showed you, this is what it looks like. Once it's been processed, you get very high surface area fibers. So these are currently on trial as the electrode support material for an alkaline membrane electrolyser by an industrial partner. And they give the same performance without a catalyst as their catalytically coated material because of the surface area. And so far, so good on corrosion. We're not seeing any undue corrosion. They're compliant. You can handle them. You can bend them. You can squash them. So they're really quite attractive. And when you put them into an electrolyser, they give you some performance benefits. So that's exciting. We can also make, and I think this is less new. I think the metals are particularly new. I think as far as we're aware, the only people that can do this. But we can also make oxides. We can make battery materials. We can make fuel cell materials. These are vanadate materials. We're interested in making these types of materials for high temperature electrolysers, actually, particularly for CO2 electrolysis at high temperature. The trouble with nickel materials is they tend to form carbon deposits, and we want to go away from nickel-based materials. Nickel is also a critical material and is something of concern. It has a carcinogenic risk as well. So we want to go to other materials so we can electrospin all sorts of things. So I just put it out there, if anyone's interested, that we'd be happy to have a conversation. Obviously, it needs to be in the context of a materials transfer agreement. And these are the things we've already made: nickel, iron, cobalt, copper, zinc, ceramic materials, and we're working on aluminium and titanium because these are interesting for lithium-ion batteries. Well, that's for lithium-ion batteries, and this is for fuel cells. They're tougher to make. So this is the M-spin story, right? It's brand new. It's just making its first hires at the moment of a couple of people. We hope that they are, and again, this has come out of a PhD project. So PhD students saw the opportunity. We worked together, created the IP, filed the patent, and have now raised the funding. Okay. And finally, just quickly, this is another company. This is not a spin-out. Actually now working with a company in the UK who are trying to replace LPG tanks with hydrogen tanks. And I'll show this one together because I think you've got some papers in your conference about hydrogen storage materials. That this uses hydrogen storage materials, solid state. And this is really about how you bring technology together to try and create something new. So there's a whole piece around how you control it, how you data link to it. We're partnered with the IIT Bombay, who've got some really neat low-cost alkaline membrane electrolyser technology. We're working on a low-cost hydrogen sensor, and in fact the first product from this company will probably be this sensor, because lots of people are trying to get sensors for a few tens of pounds rather than a few hundreds of pounds. And so that's something we're working on. And University of Nottingham, David Grant, some of you might know if you work in this area, is partnering with us on the hydrogen hydrides side. So again, I think this is an interesting approach as well. So I'm not the inventor of this, but I'm working with the company to try and help them integrate different bits of technology together and package it up in an innovative way. And there is some innovation around this as well, particularly on the control side. Okay, so I'm conscious of time. This is my only slide on my personal thing, right? So I just try and sort of draw some personal observations, and that's what they are. Everyone's experience is different. For those in the room in the academic side, right, and you're trying to deliver impact, we're all measured on how much impact we deliver. Spin-outs are certainly one of the ways to deliver impact, but they're not the only way. And just please remember, you can license your IP, you can simply publish your papers, and people can go and work for companies. That is an equally valid way of delivering impact. So it's been 40 years this year when I finished my PhD, and I've been involved in 4 companies. So that's one every 10 years. Okay, I published 300 odd papers. I don't have quite Richard's volume of output, but you know, of my 300 odd papers, you know, most of them are really interesting, I hope, academic papers, but they haven't got a lot of commercial value. So the point is, an idea has to be very distinct and before you can commercialize it. And for goodness sake, if you do think it's distinct, don't publish it, right? Because once you've published it, you've lost it. But not only that, and this happens a lot in universities, that people say, this is really clever. Yes, it is. How do you make money from it? So it has to be monetizable, right? It doesn't matter how clever it is. You've got to be able to find a way of making money. You've got to be able to monetize it. Spin-outs are quite glamorous, right? Everyone wants to be a CEO, but they're really hard work. And they take a lot of work. And on average, globally, only 10% of university spin-outs are still in business 3 years after they've started. So 90% will fail. Imperial, I think we're at 30% still active after 3 years because we have a good ecosystem and we benefit from our location, I think. But whatever happens, you will learn a lot. But please don't enter into it thinking you'll become wealthy. Right? It has purchased our house, which is very nice. But that shouldn't be the way you enter into it, right? It probably won't make you much money. So again, on the academic side, you have to balance the time you spend on this with your other academic endeavors. It's really important that you have that. Investors back people. So the team is hugely important. Right? So building that team of people with different disciplines and perspectives is very extra, not only technically, but also commercial experience is really important. I think this is a big one, right? So occasionally academics have an ego. Sometimes, surely not. Okay? The trick is when you're the inventor of something, you have to be prepared to walk away because someone else can run with it better than you can, perhaps. There are one or two people who've gone on to be hugely successful inventors as well as CEOs, but they're quite rare. And finally, and I think this is a case here in Hong Kong anyway, but with HKU I suspect in particular, the university can help. I mean, the university is here to help with this process. I think you probably have quite a good ecosystem here at HKU to help you on that journey. But if you've never done this before, you really don't know what you don't know. And there's a lot of things that really matter around legals, and things that you need to be very clear about. So you're getting some help with that. So I hope I've shown you that electrochemical technologies are important. They sit at this interface between molecules and electrons and molecules. So that is a key part of the energy transition. And I hope I've shown you that we need both materials innovation and device innovation and manufacturing to couple all this together. And again, I reinforce Richard's point, right? This is about partnership and it's about collaboration. And if we can work together in any way, let's have that in mind. I absolutely, of course, and you saw the photograph of Ceres, right? This is not me. This is many people of which I have been but a part, and many colleagues in the university and in the companies, and the people, of course, who fund this work. So thank you very much for your attention.
Thank you very much, Professor Blandon, for giving us so interesting and stimulating talks. And I think being your student is very rewarding, not only in publishing paper, but also maybe become a
several of them
CEOs.
Are now. Yeah, some
so
of them.
I think we need to learn quite a lot during the next few days, so that we can learn more about how to convert our research to commercialize, to become a very useful product.
Yep.
I think we have a couple of minutes that Professor Blandon is happy to answer some questions from you. May I invite you to sit down here?
Oh, sure.
Maybe. Yeah. Okay.
Our Fraser will ask me the tough question.
This lady first.
Hi, so I'm actually still just a year 13 student, but the way you delivered this talk, I was able to understand everything so well, so thank you so much. My main question is that there's a lot of concern about safety with hydrogen, and especially with the high temperature fuel cells. So I want to ask, with commercialization, did you have any issues with the safety of your product?
Yeah, it's a really good question. So firstly, actually running at high temperature is safer than running at low temperature because hydrogen will combust, right? So at high temperature, it burns automatically. Obviously, that generates heat. But at low temperature, the hazard with hydrogen is if it leaks at low temperature, not if it leaks at high temperature. Because at low temperature, it can leak, gather in roof voids, and then it has a very, it will combust at a very low volume fraction, right? So it has what they call a wide flammability range. So it can burn over quite a wide range of gas mixtures. So that is the hazard. So you obviously don't want to leak hydrogen. And there's no reason that you should leak hydrogen. Because you can build from an engineering perspective, you can put in enough controls to not leak hydrogen. So then the question is, what happens if something fails and breaks, and how do you know then you've got a leak? So that's why you need hydrogen sensors. In the same way that if you have a gas boiler, and I don't know how many people here have gas boilers, probably less, but in the UK we have carbon monoxide sensors. Because again, if you have a carbon monoxide leak off something burning methane, it's very toxic and it can kill people, and it does, sadly. So you have a sensor so you know that it's there, it shuts everything down. The same for hydrogen, you have a hydrogen sensor. Now the reason we're interested in low-cost hydrogen sensors is today's hydrogen sensors are really designed for chemical plants or safety critical systems, and they're thousands of dollars each. What you really need is a low-cost one that can be used not in a safety critical environment like a chemical plant, but in a more standard environment like a home or a garage or something. And then you need low-cost sensors. So you'd need a sensor to know if it was leaking. But it's, the engineering controls here are such that it would only leak if there's been some significant failure. You have containment, you have all sorts of safety systems wrapped around these things, in the same way we do with all other fuels. So all fuels have hazard. Hydrogen's hazards are a little bit different. Again, if you think about hydrogen in a vehicle application, so gasoline is a very hazardous material. We're used to it. If it doesn't obviously combust like that, but if it leaks, it pools, and then you get a vapor, then the vapor ignites. Hydrogen, if it leaks, is lighter than air. So if it leaks outside, it's really not very hazardous at all. It just dissipates into the air. Again, the risk is if it leaks inside and gathers in a roof void. So you would always have a sensor there. To tell you. So it's a combination of engineering controls and sensors. It's a very good question. And it's, at the end of the day, we need to build systems that don't leak for lots of reasons. And there's no reason we can't, but we also then need some measures around it in case there is a failure. Does that help? Yeah. Go. No, I'm pleased to say that's not. So these, you don't approach these things lightly, right? So there is a whole set of processes around warranting equipment. It goes through extensive trials by third parties. You have what are called HAZOP processes, which are a classic chemical engineering process for identifying potential failures and mitigating them by design. So all of that is done as part of the product development cycle. It's the bit that you probably, unless you've done an engineering product development program, you're perhaps not aware that this happens for all goods and all things you buy, right? But it's a really important part of both testing and questioning, well, what could happen if this happens? And how do we design something so that if this failure happens, it's mitigated? And that can often drive a complete redesign of a product. And that's the way it's dealt with. Yeah.
Professor Armstrong?
Okay, well, yeah. Nigel, I found that a remarkably inspiring lecture. And I don't think I've heard a talk which was by an engineer who could talk about the business aspects and educate us all on that. My question is really, you must have had to deal with negative decisions throughout all this time. How do you deal with that? Is it simply, as I would possibly put it, have sufficient ego that I would know, look, my invention is really good, just no one understands it. And you keep pressing on because you're confident in your own idea.
Well, I think it's a combination of things. So firstly, I think you've got to be resilient. I think that all academics have to be resilient, right? So if there was one characteristic, we were talking about funding, all academics talk about funding when they meet, right? But academia is all about rejection. Your paper is turned down, your grant is turned down, right? It's about managing rejection. I say that to all my younger colleagues. When you're rejected, don't take it personally, right? It's all about managing rejection and being resilient to that rejection. And so it doesn't mean your ideas are bad. It just means that you've not communicated them adequately. Neither does it mean most of the time that the reviewer is stupid. Sometimes it does. But mostly it's because you haven't communicated yourself correctly. So when things are pushed back, why were they pushed back? What did we not? And often it's because you've not made the message simple enough. Because most people, particularly when you're pitching ideas, so in this room, people are used to, opening their mind up to quite complex processes, quite complex things. Sadly, well, it's just the fact of life, right? That when you're pitching something, people have got 5 minutes, they've got 10 minutes. They're going to decide like that whether they, and so the distillation of the message is key. And where are you distinctive, advantaged, and beneficial? And what, because they're hearing 100 of these a week. So and it's quite helpful for how you write your papers, right? So what's the key piece of information that you're trying to distill? And I always say, when things get pushed back, you think, why did it not work? What can we do to improve it next time? And I think that's a useful message in general. Occasionally, I remember pitching Ceres in the very early days, and the guy said, remind me how many watts there are in a kilowatt? So sometimes you think, okay, I couldn't do much about that. But mostly it's because you haven't communicated it clearly, and you haven't got your narrative. And you naturally assume that what you're doing is important, but you've got to remind people why it's important.
Thank you, Professor Brandon. Very, very inspiring talk. Thank you very much. So I would like to ask, it's amazing to see when you become the advisor of Ceres Power, the value of the company raised from 1 million to now 350 to 400. So we, from our group, we also had startup, and we actually at the spot, at the cross point, internally, we want to make a decision which way to go, either through patent IP licensing or develop a product that we can commercialize it, partner with those major players in the field. What was the rationale behind when you made this decision or made this suggestion to the company on IP licensing?
So firstly, let me be clear. The fact I joined as an advisor and it's now worth that money is that there isn't a direct correlation, right? I was part of a piece, and you saw the number of people involved, right? So wiser people than I were very involved in thinking that commercial framework. I was, in fact, part of the decision that got it wrong, which was to do the product development, right? So let's just be clear. Other people take the credit for that. However, I have learned by being part of that process, and I can now bring to the other companies that I'm working with, is really, it comes back to this question around your business plan. And as soon as you develop a product, you're in competition. And that might be the right answer. As soon as you're licensing something, you're an enabler, which might be the right answer. I think it's really thinking through what the market is and how you're going to access that market. There isn't one way that's better than other. It depends what your innovation is. It depends on the market you're entering and how you're going to enter it as to what might be the right approach. We can talk about offline, right? Yeah.
Yeah, again, I want to see the accolades as a great, records of turning academic challenges into practical applications. But in a kind of a continuing phase, what I want to probably understand more is how you continue to develop your academic career. This is particularly true for younger, colleagues.
Yep.
Yeah, academic career in a way to support, the spin-out initially.
Yep.
Particularly when I talk about products. And products only have a lifespan of a few years, then will be surpassed either by our own further invention or by others. Hence, to maintain that continuous improvements in product or technology or processes would be important. But it's difficult to properly balance.
So, yeah, look, it's an important point. And I kind of tried to mention in the sideline of my talk, right? So, again, let me give you a personal experience. So in the early days of Ceres, when I was the CEO, I would go into Imperial College in the morning and do my teaching. I would jump on the train and go to Ceres, which was in the south of London, and do my company stuff. Unfortunately, as a consequence of that, whilst I was doing my teaching, I wasn't writing research proposals. And my groups, I suddenly realized all my funding was ending, right? So, and fortunately, I got myself out of that hole, and I got some proposals, and they were successful. Particularly academics in the room, you've got to balance. You've still got to publish. You've still got to win grants, and you've got to do the company stuff. So you just have to be rigorous about allocating time to those things. You shouldn't put all of your eggs in one basket, as we say in the UK, right? You shouldn't put everything into the spin-out. That doesn't mean you can't throw yourself into it, but you've got to throw yourself into it. But it's getting that balance right between those things. That's the first thing to say. And secondly, that's why you have to walk away sometimes, right? Other people have to run with it, perhaps, right? Because you've got other things to do, right? So I personally enjoy starting things. And I've been reasonably good at helping to develop them, but I absolutely don't want to run a £350 million value business, right? That is a full-time job. It's not, other people are much better at it than I am. It's not what I want to do. So you have to be honest with yourself. And everyone's answer will be different because it depends on what gets you out of bed in the morning. But there's only so many hours in the day. How are you going to spend that time? But you can't, you really do have to balance it across the different duties and responsibilities. That said, a successful spin-out in today's academic climate is a big tick. And I have no doubt that my academic career has been enabled by that, not held back. So, many people publish many more amazing science than I've done. I'm more known for that than my science. I think is okay. So I think it's a bit of luck and a bit of effort and a bit of all these things. But absolutely, time management is the key asset in this journey.
Okay. Because of the time, we have two more questions. One, you and the other lady.
Thank you. Professor, this is a fascinating talk. In one of your slides, you talked about investors in your startups, that investors don't just look at what you do, but also the team that you put together.
Yep.
So in the 4 different startups that you're involved in, how do you go about finding the right team with the right skills?
Yep.
Yeah, thank you.
Well, look, it's not an easy thing to do. I think if you're at HKU or wherever you are, I think your academic ecosystem can help. So, obviously, I say obviously, but now I'm reasonably known, right? So, I can sort of make my own contacts a little bit more. And I know some investors, and I can talk to people. But if you don't have that network, go and speak to your university colleagues, even other academics who've done a spin-out, or your tech transfer office. I don't know how it works here, but if you've got a good one, they might have people they can introduce you to who can help with that journey. I think it's just bearing in mind that you do need a balanced team. So that is something, in an ideal world, you need a tech person, a finance person, and a business person, right? But it's early on, you can't afford money for big salaries either. So you can often find an industrial person that's run a company that can probably bring you enough legal and financial experience. That's one. And then as the academic, you're probably the tech person. So that's not a bad starting point. But preserving cash is key in these early days, right? So you're trying to not pay people. You can give them equity. You can do everything you can to preserve your money, because you raise X, but you're probably going to need 2 or 3X. So as soon as you start, you're starting to burn cash, right? So the clock is ticking. But yeah, so talking to people, network. And one more question, yeah.
Thank you, Professor. I have a questions about the ion exchange membrane. So as we know, the ion exchange membrane plays an important role in battery. And for some commercial membrane like AEM or CAM, they cannot be placed in air environment for a long time, and its structure will be destroyed. So if now I want to use gas electrolyte to replace the solvent electrolyte, so is there any membrane can keep stable in the interface between gas and
so
solvent?
what? Sorry, I missed the application. So which is this, an electrolyzer or a battery?
It's battery.
Okay, right. So a classic lithium-ion battery, you mean? You mean a lithium-ion battery or something else?
Half of the battery chamber is gas, and then another chamber is.
Okay, all right, okay, fine. Well, look, so the first thing I'm going to give my disclaimer, right, is I'm not a membrane person. I'm an electrochemical engineer, and I will reinforce the comment you make that membranes, I want to add this to the list of technology wishes, right, are better membranes. So that's another critical enable opportunity for science to contribute in general, is around ion exchange membranes. I mean, it's a huge opportunity and need. So at the moment, in the flow battery work, we use commercial membranes, okay, rather than anything that special. And they're adequate for what we're doing. So, you can, and naphthion and its variants are the types of things we use in the flow battery membranes. I know that there are groups in some parts of the world, including in China, where they're doing some really, because there's huge, big vanadium flow battery programs in China, right? I'm sure you're aware. And they've got these microporous membranes, so they're not ion exchange, and they look quite interesting. But for hydrogen, for a hydrogen liquid membrane, you can't use microporous because the hydrogen still goes through the pores, whereas with the liquid you can. So I'm slightly ducking your question because I don't want to give you a silly answer, but membranes matter a lot. I absolutely agree.
Okay, thank you. Thank you, Professor.
Okay, being the MC of this talk, I have the privilege of asking the last questions, a quick question.
Yeah.
So, wow. I would like to ask how Imperial College helped your commercialization of your product and also setup of your startup company.
Sure.
What is the role of
okay,
university?
Okay, so that could be quite a long answer, but let me try and be succinct. So it's changed over time. So when we did Ceres, which was 24 years ago, there was very little ecosystem to help. So we sort of made it up, right? But if I look now to where things are, we have a much more sophisticated process by which we assign IP. So it's all on the website. You can go and read it. So we have something called Founder's Choice. That means that provided as an academic you sign up to that deal, college takes 10% of the equity. You have 90% of the equity. There are standard template terms for all the license agreement and everything. So it's streamlined. We spin a company out a month. So you need to get, it's all about pace, and it's all about, at the end of the day, this is a bet. From a university perspective, you're betting on volume. So you want them to come out like that. You don't want a set of complicated negotiations for every company. So all of the college terms, I think, are on our website. They're standard because we make them open to our investors. And so that's one way they help. I think we have a reasonable reputation. You have a reasonable reputation. So reputation helps because that you've got brand association. We have a good network of investors. So the one thing we don't have is our own money to invest. And in fact, that's the one thing that we're now changing. Oxford have got a pipeline. Oxford have their own fund. UCL have got their own fund.
Still not a great amount of money.
No, but it's better than nothing, Fraser. But we're also in the process of setting up our own fund. And that will also then help accelerate things along the line. So we offer training. I'm sure you do the same here, but every student, we have lots of student startups as well. So anyone that wants to can go and get training and support around the legals, around how you write a business plan. We also run, and I help set it up within Imperial, a network of advisors. So these are mentors who come in from outside the university, experienced industrialists more likely, who can help academic colleagues, if you like, improve their vision for the business. So we're trying to improve the quality of the offering to the market and making colleagues think about this point about it may be clever, but can you monetize it? So that kind of constant, how are you going to make money out of it? By people who understand how you make money out of things, right? And understand the market within their sector. That is another big help. So all of that together, I think it's an ecosystem that you can create that makes it easier than not having it. But it's still not very easy, but it makes it easier.
Okay, I think this is the end of this distinguished William Mong distinguished lecture, and I would like to thank all of you for your active participation, and may I ask you to give a big hand to our speaker today, Professor Brandon. Thank you very much.
Thank you very much.